everyone. So, as Prannoy said, my name is Juan Pablo Gevaudan, but please just call me JP, it's much easier. I'm an assistant professor at Penn State University in the Department of Architectural Engineering. And today I'm very excited to be talking to you about the work from one of my PhD students, Delaney Link, on advances in thermodynamic modeling for this magnesium-based cements. So we're going to talk a little bit about like why magnesium-based cements, why do we actually care about them in a global context, and how the thermodynamic modeling comes into play. This is part of a larger effort by RILEM, the Working Group on Magnesium-Based Cements, MBC. I lead the Working Group 1, which is on dissolution and mobility of magnesium ions, because we believe this is a really important aspect that we'll need to overcome to actually make these magnesium-based cements an actual applicable cement. So we're going to talk a little bit more about that. Today, just going to introduce a little bit about the advances in thermodynamic modeling, some of the challenges that we're facing there, the methodology on how we're actually trying to use experiments to validate our simulations. So we just heard from our speakers that it's really important, right? All models are wrong, right? But they're useful. And a way to make them useful, more useful, right, is to actually verify them with experiments, right? We need to check that ground truth. Now, we're going to understand a little bit about additives. There's a lot of work right now. It's really exciting. We're using clays. We're using organic acids. We're using additives to really control the dissolution behavior of magnesium oxide, right, or magnesia. And then this is ongoing work, which just started this semester. So there's a lot of stuff that we're doing. So I'm going to give you a little bit of a hint into like where we're going, what are the future directions, how is this plugging into greater work. Right. So, sure you all have seen this, but magnesia is counted as the first carbon-negative cementitious precursor. Right? Why is it the first one? It's because we have the ability of producing magnesia from non-carbonate rocks, such as magnesium silicates, or foresterite being the mineral there. And we also are thinking that we can have these processing technologies that can utilize renewable energy to create this magnesia. Right? So this is the main motivation for wanting to study more this magnesia as a precursor for a cement. Right? Now, the problem is that magnesia has a very low solubility limit, lower than calcium oxide. All right? Its dissolution rate, you can see, it's very slow. And that's an asterisk there. We're gonna see a little bit more about that. Now, a key issue is this. So this is a recent paper that was just published on the micro-CT of periclase, which is just magnesia, not found in nature. And they just flow water. And what you're seeing is that after 140 minutes, right, all the red that expands the volume is brucite. Okay, it's magnesium hydroxide, right? Because the magnesium is just hydrating, right? If this is happening in a hardened cement, bad news. We all know that, right? We do not want that. So we need to not only control the hardening rate of these cements, which is usually pretty fast, right? But we also need to control this reaction. So how are we going to control that reaction? So that's what we're going to be talking about. We need to understand the reaction to then engineer the dissolution of magnesia to prevent this magnesium hydroxide precipitation. Once we do that, we have unlocked one of the key barriers in actually making the cements an actual practical reality. Right? Right. So, let's look a little bit about, so I'm a cement chemist, so I need to show you at least one chemical reaction. Alright? So, here we have the main chemical reaction that we're dealing with, right? It's just the hydration of magnesia. It's going to dissolve and give us this magnesium ions, right? And hydroxide ions in solution. Of course, these are going to find each other, and they're going to start creating this brucite magnesium hydroxide as a precipitate form, right? What we just saw. Now, what happens is that we can actually add these organic acids, which lower the pH because they're an acid, right? But they do something really, really cool. they can actually create complexation for the magnesium ions that we're seeing here. So they can complex with the magnesium ion, right? Create this, what we call ligands, and take them away from the surface that is dissolving for that magnesia, right? So what we're trying to do here is actually trying to use thermodynamic modeling to predict how this reaction is happening. How is it helping the dissolution of magnesia, or is it helping the dissolution of magnesia? But by how much? Can this actually solve our issues in controlling this reaction? And can it actually be that silver bullet that we're hoping for? Right? So, it is critical to understand that the hydration pathways need to be identified. Okay? So we need to know what are the hydration pathways for this system. And that's particularly because we are using FRIXY. Okay, so if you don't know FRIXY is a geochemical simulation code, and we need to tell it what are those reactions that need to be solved to create this equilibrium model result, right? So some of the things that I wanted to talk about is we're going to be looking at the addition of clays and organic acids as its additives to control the dissolution of magnesia. We're also going to be looking at what dissolves, what precipitates, right? And I'm not going to jump to those results because they're really, really cool. So I'm going to hold my excitement for that. And then the other thing is we want to actually talk about the solubility of magnesium oxide, right? Like that's what we're going to be looking at to see, is it improved, is it not improved, right? Some of the questions that we're hoping to answer by looking at this is, how reliable are geochemical modeling tools like FRIXY? Can those help us mitigate some of these challenges? What are the reliability of the databases we have right now? We use periclase in geochemical modeling, but does that really represent the lightly burned magnesia that we use, right, in these cements? And also, how can experiments actually expand our modeling capabilities, right? So, in order to do that, we're going to be doing something here. We're going to be integrating the experiments and simulations. That's what we're here in this session, right? The first thing, like I said, we're going to be using thermodynamic simulations, FRIXY, Data 18 as our database, as well as Mintech for some of those magnesium dissolution reactions. Now, the simulation side is a batch reaction that we're trying to do. Okay, so that means that we take a beaker and we're just going to make sure that it's well mixed, and then add our magnesium oxide, 25 degrees Celsius, 1 atmosphere, right? Standard conditions. Now, one thing that we're doing in this thermodynamic simulations, we're adding sequentially the amount of magnesium oxide in different solutions with these additives. We're assuming a couple of things, right? Remember that this is a thermodynamic simulation, right? And by adding sequentially our magnesium oxide, we're almost cheating here, all right? We're trying to approximate the reaction rates, right? Kinetics, which is not really the goal. It's not really what thermodynamic modeling is really done for, right? Like used for. But we can do that if we assume that we have congruent dissolution and that the equilibrium for these partial reactions is reaching in real systems, this equilibrium is being reached really, really fast, right? So those are our assumptions, and those are key assumptions there. Now, in the experimental side, we have this lovely piece of equipment. It looks fancy. It really is just a beaker. Okay, there's 2 beakers in there. We're controlling that temperature to make sure that it's at 25 degrees Celsius, just like our model. We're making sure that there is gas flow, inert gas flow, so that we don't have any like carbonation reactions happening, so we can control for that. And then it's well steered, so those like big tubes right here. That's a metal thing. Okay, those 2 things right there, those are just paddles, just mixing our beakers, right? So just to make sure that we have a batch reaction going on, right? So we can control the reactions, and we're going to be measuring the pH right now. That's the data I'm going to show you. But we can do other things, right? We can actually take samples of the aqueous solution, so we can keep track of like the dissolved chemical species. We can put in an FTIR probe to look at what reactions are happening, what bonds are being formed. So we can do much more, but I'm just going to show you the pH and see, does the pH in the experiments match the simulation? All right? All right. So let's dig into the results. The first one, pretty simple, right? We're just going to put in some magnesium oxide in water. What is the dissolution? Let's look. So what we see here is the dissolution, as we know, is really low. And it reaches equilibrium by precipitating magnesium hydroxide. We know this. This is great. Okay. That's fantastic. Now, if we look at the saturation indices in this particular simulation, we see that brucite is more likely to precipitate and magnesia is more likely to keep on dissolving. And that's key. Because, again, remember, if it's a hardened material and magnesia is dissolving and precipitating brucite, that expansion is going to crack our material. It's not what we want, right? But we know this. So now let's look at what happens when we add some clays, right? So interestingly enough, right? So when we add between 0 and 15 weight percent kaolinite, right? There's not much improvement in the dissolution of the magnesium oxide, right? We're all the way down here. However, when we add 30 weight percent or even 60 weight percent of kaolinite, right? Or we replace magnesia by kaolinite, right? We can increase the dissolution quite dramatically of the magnesium oxide. This is fantastic because one of the things that we see is thermodynamically is favorable to precipitate MSH and mineral forms of magnesium silicate hydrate. That's what MSH stands for, such as sepulite or talc or chlorite and others. Right? So this is great. And we went into the literature and we were like, okay, does this actually make sense? And if you see the Elena Bernard, who is the co-lead in the working group for RILEM, we checked out her research, published in CCR just this year, and we see exactly the same thing. For her experiments on 64% clay with magnesium oxide, we see the formation of this MSH phases. So that's great. Like, this makes sense, right? Fantastic. So then, another thing that we were asking is, well, addition of acids, right? Like, what is the effect of organic acids, such as acetic acid or citric acid, on the dissolution of this magnesium oxide, right? And what we're seeing here is that in the absence of acids, is that yellow line here, that's what we saw before, right? When we add just 5 weight percent of either of those two acids, we get an increase in the dissolution of that magnesium oxide, which is fantastic because we can think about these acids as admixtures for this novel cement chemistry system. Right? Now, why that works? Well, we looked into our thermodynamic modeling, and it's something that we're actually trying to validate with experimental studies. The formation of these magnesium organocomplexes in solution. Right? So remember that I was telling you about the complexation reactions that were happening. So those were definitely something that was predicted by our thermodynamic models, but we need more experimental data to actually think about and understand how these happen, right? Where do they go? What is the mobility of magnesium? What are the effects on the precipitation of some phases here? Right. So, one thing I wanted to mention here is that when we do increase that addition of citric acid and acetic acid, what we see is that the brucite is least likely to precipitate when we actually use citric acid. One of the things why that may actually make sense from our thermodynamic models is because citric acid actually is a ligand that has 3 places where it can actually complex with magnesium ions in solution, right? So that's really cool. It has 3 teeth, basically, to bite onto magnesium ions in solution, and that's why we believe, and of course we need to experimentally validate this and actually study this, that we can prevent some of that brucite precipitation with citric acid much better than with acetic acid. And this lines up with some of the results that we're seeing in the working group for RILEM as well. So, we're all here to see how it actually matches up with our experiments, right? So in order to validate some of these results with experiments, we use our easy match that I just introduced you to earlier, and we did 3 separate experiments here, and we're going to utilize pH to really track the reaction rates of this 3 different batch reactions, and really look at, did it achieve this equilibrium, or is it matching our simulations, right? So in the first reaction, it's just magnesium oxide and water. Second reaction, we have 28% acetic acid. And in the third reaction, we have 28% citric acid. Okay? The same amount of magnesium for all of them. Right? So, here are the results. Reaction rates are rapid in this system. So the lightly burned magnesia that we use reacts really, really quickly, in minutes, right? It reaches equilibrium in just minutes, which presents a problem. But perhaps it also presents an opportunity, and I won't talk about that too much. But one of the things that we see here is the pH value in the y-axis and then the time here in the x-axis, right? When we actually use just the control, just water, we're reaching a pH experimentally about 11. Right? But when we look at the simulations that I was showing earlier, the pH of equilibrium is far higher than that. It's around 12 to 13. Right? And you can see that it also repeats for when we're using citric acid or acetic acid. And in particular, when we add such a high amount of acids, actually the pH stays pretty low. And it never reaches, well, in this time frame, and we did experiments for longer, doesn't actually go back up to reach that 13 predicted pH. So, in line with what we were just discussing in previous talks, experiments are really important to validate or understand, can our models actually predict actual conditions? Right? So one of the things that we believe is happening here is that we're not having a complete reaction as predicted by thermodynamics, right? Remember, this is equilibrium reaction, right? So we believe this is a partial reaction, an incomplete reaction of the magnesium oxide, which could be being caused by the clustering of precipitate phases around the magnesia, so preventing it from further reacting. Of course, we'll need more experimental validation to actually prove that, and hopefully I can present on that work in the future. But some of the further steps that we're also discussing here or thinking about is further dissolution, kinetic experiments where we're looking at magnesium ions over time. So I told you about, that easy sampler idea of just sampling the solution over time to look at what are the ions in solution. You can validate that through a thermodynamic modeling as well. We can use that FDIR probe that I talked to you about as well to better evaluate the model's reliability. And also, we need to be thinking about the databases. So all the databases that we use right now is the SEM-Data 18, but also we use a lot of geochemical modeling databases, which may not really have the right reactions or the equilibrium constants for things like a lightly burned magnesia, right? Because it's ferriclase, it's a naturally abundant magnesium oxide phase, which may have different equilibrium constants, perhaps. So we need to validate and really look at our databases a bit further. And also, we need to determine the precipitated phases and so forth. So that's ongoing work that we have right now, and as we modify the systems. With that, I'll leave it up for questions. I do want to, again, thank the PhD student, Delaney, for doing all this fantastic work, and hopefully more on that to come. Thank you.